this today is because chapter 11, basically we deal with a lot, we're dealing with area and parts of circles and surface area and volume of three-dimensional shapes, that sort of thing. And what the book is assuming, because Big Ideas does this, Big Ideas starts in like 6th grade, 7th grade, 8th grade, 9th grade, then Algebra 1 and Geometry. They know that in the 6th, 7th, 8th grade units, you learned all the basic formulas for the areas of all these basic shapes. By the way, computers don't need to be out right now, phones don't need to be out right now, so let's go ahead and close them up. And the fact is that some of these formulas are going to be super easy. You're going to remember them in a heartbeat and have not a problem with them at all, but others may be new or a little bit different, something that you might want to jot down in your notes right away on your front page of your packet, so you always have these formulas with you, because you will be expected to know these formulas. And I don't want you to walk into it just saying, well, duh, of course you know the formulas. I want to put them on the board at least once for you, give them a chance to write them down so that you know what the formulas are for basic areas. And there's actually one or two kind of interesting ones that you probably haven't seen before that we're going to do today. So let's start with the really basic formulas first. Let's start with our most basic formula we can think of, a rectangle. Okay? Area equals base times height, or length times width if you want to put it that way, right? That's a rectangle. That's one of the shapes you'll need to know how to find the area of. Ooh, we're starting tough, aren't we? A square, just to get a nice perfect square here, okay? A square, we can also do base times height, but since all four sides of a square are the same, we can also say the area just is one side squared. Side times side, side squared, right? There's actually another formula we're going to get for that in a minute. A parallelogram okay, your basic old parallelogram, the area is the same formula as a rectangle, still base times height. The difference is the height in a rectangle is one of the sides, so is the base. In a parallelogram, the height is the perpendicular distance between whatever I'm calling my two bases. So the height is generally not a side in a non-rectangular parallelogram. So it's still base times height, but the height isn't always given to us. And what that leads to in some types of problems is, guess what? Pythagorean theorem, or SOHCAHTOA, or something like that to help us solve that right triangle in order to find that height. Sometimes it's given, sometimes we've got to work it out. Okay. A rhombus, kind of hitting our quadrilaterals here. Okay, here's our rhombus. All four sides the same. Now, we could, because it's a parallelogram, we could do base times height. All right, we could do that. But there's a special formula for rhombus, and it comes from the fact, I'm not going to work through all the math of it, because you don't want to listen to that anyway. Okay, we know that in a rhombus, the diagonals are perpendicular. And so we've got these four right triangles in here. So rhombuses give us actually a special formula for the area. The area is diagonal 1 times diagonal 2 divided by 2. So we actually multiply the lengths of the diagonals to find the area of a rhombus and divide that product by 2. Now, because a square is a rhombus, we can use the rhombus formula here. But since the diagonals are the same in a square, it's actually just diagonal squared over 2. Most people don't bother memorizing that. They just remember diagonal 1, diagonal 2, and just happens they're the same. It's fine. So squares actually have a lot of choices, depending on the information we're given about the square, what we do with it. Our final quadrilateral, in fact, I'll do this on a new page. Our final quadrilateral that we have to deal with is a trapezoid. The trapezoid is a little bit different. Okay, and the way we understand the trapezoid is really by first looking at the triangle. Oops, I wanted a solid line. Okay, so here's some random triangle. And we know the area of a triangle is what? What's my formula? Base times height divided by 2, right? Why? Because a triangle is half of a parallelogram. Okay, that was fun. Okay, you get the idea. A triangle is exactly half a parallelogram, so what do? We use a parallelogram formula divided by 2, right? Makes sense. All right? So that's our basic triangle formula that we've known since, what, 3rd or 4th grade. Base times height divided by 2. So in a trapezoid, what we're going to do is we're going to say, okay, let's divide this into 2 triangles. Now, the 2 triangles are not at all the same. Okay? This one's acute, this one's obtuse. So they're not even close to the same triangles. But they do have the same height. The height out here, we got to kind of extend. You've done this before. Okay, they have the same height, the same distance between the bases. So if I call this one base 1 and this one base 2, the area of this, we get base 1 times height divided by 2, plus area of this triangle, base 2 times height divided by 2. But I can factor out the height over 2 because that's common in between the 2, and we get our formula. Height over 2 times base 1 plus base 2. So trapezoids are a little bit trickier. But I want you to see a lot of people just drive straight to the formula. Okay, it's base 1 plus base 2 times height divided by 2. Well, I want you to understand why that works. It makes sense, actually, because it's made up of 2 triangles. Okay? The one more special one I want to get to, oh, sorry, almost forgot the kite. Oh, I did forget a 4-sided shape. Not a kite. Kite uses the same formula as rhombus. Diagonal 1, diagonal 2 divided by 2. Okay? This or kite. So that works for rhombus or kite. Okay? So that one serves double duty. Yay! Same formula for 2 things.
Wait, is that D1 minus?
D1 times D2. Multiply them and divide by 2. Multiply the diagonals. The last polygon we want to talk about is a special one, the equilateral triangle. I want the wrong, that's why. There we go. Okay. The equilateral triangle. Now, equilateral triangles get their own special formula. We could use base times height divided by 2, of course, right? But there's a shortcut formula that can really save us some time with equilateral triangles. And basically what it comes down to is this idea, all right? If I say that this is a side, each side is S, right? Then what's every angle in the equilateral triangle normally? 60. And this is 90, so this is 30. Oh dear, what do we have? A 30, 60, 90 triangle. Yay, back to right triangles. But what do we know? We know that then this would be S over 2, and this would be S over 2 times the square root of 3, wouldn't it? That's our formula for equilateral triangles. If you don't remember that right now, it's a good place to remind you of it because you're sure it's going to show up in the final exam again. Okay, N, 2N, N root 3. Okay. So, it took forever and I've been over in case you missed that. So, What's the area going to be using base times height divided by 2? It's base times height times 1/2. Divided by 2 is the same times by 1/2. When I do that in the numerator, I get an s, and the square root of 3. So side squared root 3, the denominator gets a 2 times 2 over 4. And so if I just know the side of an equilateral triangle, I can use this formula to find the area. Side squared root 3 over 4 and 4. Now, everyone's like, oh, I'll never remember that. Okay. Here's a little hint on how you remember it. Can you count to 4? Okay, then you're pretty much done. Okay, but if you can count to 4, we go 1, 2, 3, 4. Oh. Now, the 1 is an S, not a 1, right? And the 2 is an exponent, the 3 is under a radical, and the 4 is down here. But it's 1, 2, 3, 4. That's all it is. Not that hard to memorize, because if you can count to 4, you can probably memorize that formula. And again, you don't have to have it memorized, but it can be a great shortcut as we move forward. Now, this idea of dropping in the altitude of a triangle and splitting it up and solving for this height is going to be one that we're going to see a lot of. Okay? They're not always going to be equilateral triangles, but they'll be isosceles triangles. We're going to do that a lot. We're going to drop in an altitude and solve the height. Sometimes we might use 30, 60, 90. Sometimes we might have to use SOHCAHTOA. These are trig functions to find that height. And that's something we're going to do. The last thing, of course, I said that was the last polygon, and it was, because we still have to talk about circles. Okay? And circles are based on, of course, radius of the circle. Everything's based on the radius. And 2 times the radius is the diameter. That was a terrible diameter. But you get the idea. We'll just make the center bigger, make it work, right? Okay. Okay. 2 measurements we need with a circle, the area of a circle and the circumference of the circle, right? The area of the circle, if you recall, is pi r squared. Or because we often write it in terms of pi, I sometimes like to write r squared times pi. Because if the radius is 5, then the area is 25 pi instead of pi 25. Puts in the right order. Doesn't matter. Same idea. All right? Circumference is just pi times diameter. Now, you may have learned this formula as 2 pi r in middle school or before. But you want to know what? When you do it that way, you've got the exact same numbers and variables in both formulas, don't we? We have a 2, a pi, and an r in both formulas. And guess what? I don't know about you, but I'm easily confused. In fact, I go home and cry most days because I'm so confused. But it's okay. I'm good with that. I've accepted that. But a way I can avoid that confusion is by using a different variable. Diameter is 2 times the radius, right? So I could just say pi times diameter or diameter times pi if you prefer. And now we've got different variables, so it's really easy to distinguish which formula is which. It's just a little trick that I use to help myself remember things. Now again, these are just formulas that are going to be used in this chapter. And for the most part, it's going to be assumed that you know them. But today just presented a great opportunity for me just to represent these simple formulas to you, some not so simple, but to remind you of them so that when we run up against them in the chapter, you're ready to go, oh yeah. In fact, I wrote that down on my note sheet, so I had all these formulas. And you're like, yeah, good times. Okay, that's it. That's all I got to talk about.